Sometimes the occurrence of one event may affect the probability of the other event. For example, the chances of student passing a class depend on whether they ace the final exam or not. This relation between two events is called dependency, and to quantify such dependencies, we introduce the concept of conditional probability. We're going to start with the definition. Conditional probability of A given B, labeled as P of a vertical line B, is the probability of event A knowing that event B has occurred. In the context of conditional probability, we call probability of A prior probability, and the probability of A given B posterior probability. In general, the probability of A given B is not the same as the probability of B given A. In the following example, consider rolling a die, and let A be an event whose outcomes are 1, 3, and 5. The probability of A is known and is equal to 1/2. Now let's consider event B whose outcomes are 4, 5, and 6. Now we're ready to roll a die, and let's say we're interested in the event A. As of right now, prior to rolling a die, the probability of A is 1/2. But imagine that before the outcome of the experiment is announced to us, someone whispers that event B has occurred. Does the knowledge of B occurring changes how we evaluate the probability of A? What exactly changes once we learn that B occurred? To understand what changes, we must look into how the probabilities are computed. The prior probability of A is computed by dividing the number of outcomes in A by the size of the sample size. So what exactly changes when we know that B has occurred? We may not know what exact outcome has happened, but we know that it must be one of the three that described event B. Otherwise, we wouldn't say that B has occurred. So event B is now the new sample space for event A. Since 1 and 3 are not in the list of possible outcomes anymore, we remove them from event A. So it can only occur if 5 was the outcome of the experiment. In other words, when B has occurred, the event A may only occur in one way out of the remaining 3 outcomes. So the probability of A given B is 1/3. In general, any conditional probability can be found by finding the restricted sample space and then finding the number of ways that the event can occur in the restricted sample space. Let's consider for the same experiment the following events C and D, in addition to previously defined A and B. And let's find some prior and posterior probabilities. The prior probability of B can be computed by dividing the total number of outcomes that describe B by the total number of outcomes in the sample space. The prior probability of D can be computed by dividing the total number of outcomes that describe D by the total number of outcomes in the sample space. The probability of B given D can be computed by dividing the total number of outcomes in D that describe B by the total number of outcomes in D. The probability of D given B can be computed by dividing the total number of outcomes in B that describe D by the total number of outcomes in B. Similarly, the prior probability of A can be computed by dividing the total number of outcomes that describe A by the total number of outcomes in the sample space. And the prior probability of C can be computed by dividing the total number of outcomes that describe C by the total number of outcomes in the sample space. The probability of A given C can be computed by dividing the total number of outcomes in C that describe A by the total number of outcomes in C. The probability of C given A can be computed by dividing the total number of outcomes in A that describe C by the total number of outcomes in A. If we write out the results of the previous computations on the same page, we'll be able to see an interesting phenomenon. The probability of A didn't change after we learned that C has occurred, so as the probability of C did not change after we learned that A has occurred. Such events are called independent. On the other hand, the probability of B changed after we learned that D has occurred, so as the probability of D has changed after we learned that B has occurred. Such events are called dependent. We provide the formal definition. If A and B are such that occurrence of one doesn't affect the probability of another, then we call A and B independent events. Symbolically, we can express the definition of two independent events by the following statements. If one of them is true, the other one must be true as well. So, if one wants to check whether two events are independent, one must find the prior probability and compare it to the conditional probability to see if they are equal. If they are, then events are independent. If they are not, then events are dependent. Frequently, students confuse mutually exclusive and independent events. Mutually exclusive events have no common outcomes. That is, the probability of A and B is equal to 0. With independent events, the occurrence of one doesn't affect the probability of another. That is, the probability of A given B is equal to the probability of A, and the probability of B given A is equal to the probability of B. As an example, consider the birth of a child. Before the sex of the child is known, there are two possible outcomes, B or G. Normally, they are considered to be mutually exclusive outcomes, and the prior probability that the child is a boy is equal to 1/2. If we ask ourselves what is the probability that the child is a boy, given that she is a girl, we will find the conditional probability of B given G, which is obviously equal to 0. So the two events are dependent because the probability of B went down to 0 once we learned that event G has occurred. So the only relation between the two concepts is that the two mutually exclusive events are always dependent. We discussed how the occurrence of one event may affect the probability of the other one. This concept is called conditional probability.